Good morning, students. The topic here is parallel processing and pipelining. So parallel processing. Parallel processing is performing simultaneous data processing task for the purpose of increasing the computational speed of a computer system. Parallelly processing means executing many data processing operations at the same time. Okay, that is parallel processing. Okay, the computers that does not support parallel processing performs these tasks in a serial order. If there are some 5 tasks to be completed, okay, 5 processes need to be completed. First process is completed. Once the first process is completed, the processor can take up the second process. Okay, that is serial processing. Parallel processing is simultaneously doing all these processing. Okay, simultaneous data processing task. So this increases the speed of the computer. Okay, so the main goal here is to increase the speed of the computer. So it performs concurrent data processing to achieve faster execution time. Okay, concurrently executing the different tasks. Instead of performing one after the other, the data processing is done concurrently. Okay, so what is the purpose? Why we need parallel processing in systems? To speed up the computer processing capability. Okay, it speed up the process definitely when than doing it one after the other. When many tasks are done parallelly, okay, it speed up the computer processing capability. And the second reason is it increase the throughput. What is throughput? It is the amount of processing that can be accomplished during a given interval of time. Okay, when the computer is designed by the designer, computer designers, the main goal is to make the computer process more, right? So the amount of processing that can be accomplished during a given interval of time, that is throughput. So to increase the throughput, we can go for parallel processing. Parallel processing is needed to speed up the computer processing capability, and that increase the throughput. When the speed is increased, the computer can perform many processes at a little time. Parallel processing at the lower level of complexity can be achieved by using parallel load registers. Lower level we mean here is at the register level. If parallel processing need to be achieved, okay, at the register level, we use parallel load registers. The register that have the capability of having parallel load. Okay, instead of one after the other. Shift registers. We know shift registers are used to shift the data serially. If there are 4 bits, okay, that has to be transferred between registers A and B. The 4 bits are transmitted serially, okay, having a single line between, single data bus between the units A and B. The data transfer is done, okay, this is serial. Serial transfer, shift registers are used. And for parallel, the same thing, okay, 4 bits. So first the 0 bit is transmitted. And once that is transmitted, the first bit, and then the second bit, and then the third bit. Okay, so this way the bits are transmitted in serial registers. Okay, if the registers have parallel load, the transfer will be done like this. As we have 4 bits, 4 parallel lines are used. Okay, so at a time, all the 4 bits are loaded in the bus, and that is transferred to B. So at the register level, parallel processing can be implemented by using parallel load registers. Parallel processing at the higher level of complexity can be achieved by having multiple functional units and distribution of data among multiple functional units. Okay, so if we need to implement parallel processing in computer, then we need to have multiple functional units that perform these tasks parallelly. Okay, having a single functional unit. Example, if there is one ALU, it can perform one of the arithmetic, logical, or shift operations at a particular time. Okay, but having many ALUs, if the system has many arithmetic and logical units, okay, the many operations, arithmetic, logical, or shift operations can be done parallelly. Having same way, increasing the number of processors the system has. Okay, this way having multiple functional units. When we have multiple functional units that can operate parallelly, that can perform the task parallelly, the data also need to be distributed to all the functional units, right? At the same time, data distribution. So definitely the complexity increases. The functional units are more there. Okay, there are many processes, there are many operating units like arithmetic and logic units. So there need to be many registers. Okay, storage need to be more for operating parallelly. Data need to be distributed among all these units. So the connections, okay, between the units will also become complex, and the operations need to be controlled. So you can imagine, okay, you can visualize the complexity of such system. So parallel processing is generally used in systems where the time is critical, okay, where the operations need to be performed in a given amount of time. Okay, that is very important there. Okay, in that case, parallel processing is used. So we need to have multiple functional units and distribution of data among multiple functional units to achieve parallel processing at higher level of complexity. So when we implement this, it results in improved resource utilization. Okay, that is an advantage here. Now let's take an example of instruction execution. We know that instruction execution has many phases, right? Every instruction go through fetch phase. Okay, one is fetch phase, and then decode phase, then the effective address, getting the effective address, that phase, and then execution phase. So in these phases, if these phases are done one after the other, serially, sequentially, one after the other, first it fetches the instruction. So what are the resources used here? Fetching means transferring the instruction from memory to the processor, one of the processor register. Okay, the register here is instruction register, fetching the instruction. So instruction register is used. The resources utilized are the processor register, where the instruction will be stored, and memory. From memory it has to be fetched, and the bus, right, the line, transfer line through which the instruction can be transferred. Okay, so these are the resources that are utilized. Now, when the fetch is over, when the instruction is an instruction register, we don't need the transfer lines because decode phase is done internally inside the processor. So that is done. There is no data transfer there in decode phase. So the buses are not needed. The buses that runs between the memory and the processor are not needed here. Okay, so during decode phase, the next instruction can be fetched. Correct? The buses can be utilized. The buses that are idle now, that can be utilized to transfer the instruction to the register. Okay. Same way, when decoding is over, it goes to find the effective address. Okay. The processor's job is to find the effective address for instruction 1. So at the same time, this instruction 2 can enter into decode phase. Okay. So this, in those computers, okay, that support parallel processing, the resource utilization is improved. Okay, improved resource utilization. Instead of having a resource idle and working with the other resource, okay, all the resources will be utilized at the same time. That helps in completing the job faster. And the second effect of this parallel processing is increased amount of hardware. Okay, for implementing parallel processing, we need to have many functional units that operates parallelly. So in increased amount of hardware. When the amount of hardware increases, the complexity increases. Okay, the connection between the hardware units need to be increased. So the complexity increases. We need a complex control unit to coordinate all the activities. Different activities are running at the same time in different units in the system. Okay, so to coordinate all the activities, we need a complex control unit, and which results in increased cost. Okay, so the cost of the system increased. Okay, so as I said, it is implemented in system where the the process need to be completed within a certain time period. Okay, so in such cases where time duration is critical, okay, in that cases we use parallel processing. So here this figure shows the possible way of separating the execution unit into 8 functional units that operate in parallel. Okay, here the arithmetic and logic unit that performs arithmetical, logical, and shift operations, okay, are divided into 8 units. The adder and subtractor circuit. This performs addition and subtraction on integer numbers. And integer multiplier. This is a circuit, okay, unit that performs multiplication. Only multiplication is done in this unit, and only addition and subtraction on integers are done in this unit. And all the logical operations, okay, and or not are done in this unit. And shift, okay, this is to shift the data. Okay, that is done in this unit. Incrementer, okay, does only the increment operation. And floating point add and subtract. The circuit performs addition and subtraction on floating point number, floating point multiply, and divide. Okay, so this way the arithmetic and logic unit is divided into 8 different units that operates independently, okay, and parallelly. So all these operations, instead of, if arithmetic unit is, if the computer has a single arithmetic unit, one of these operation can be done at a time, okay, performed at a time. But in this case, as it is divided into different functional units, all these operations can be performed at a time. When the no when shift unit shifts the data, incrementer unit performs okay, incrementation on the same data or different data. So then we need to have the different processor registers to store a lot of data, and complex connection. Here the connection between these units to transfer data between, and okay, so the complexity increases. So this way parallel processing can be achieved by dividing the functional units or having more number of same units. So the complexity increases here, the number of hardware is increased, and so the number of connection between the units increases, the complexity of the system increases. Okay, and control unit, we need a complex control unit. Instead of having a single control unit, it need to be increased, okay, to control all the activities that is happening parallelly in different units. According to M.J. Flynn, the classification of computers based on the parallel processing, the computers that support parallel processing can be classified by the number of instructions and data items that are manipulated simultaneously. Okay, he classified the computers based on the number of instructions and data items that are manipulated simultaneously. So what is instruction stream? The sequence of instructions read from memory constitutes an instruction stream. And data streamers, the operations performed on the data in the processor forms the data stream. The sequence of instructions read from memory we call instruction stream, and the sequence of data, okay, and the operations performed on the data in the processor constitute data stream. According to Flynn's classification, okay, the computers are divided into 4 major categories: SISD, SIMD, MISD, and MIMD. SISD is single instruction stream, single data stream. Okay, means the computer that uses this configuration, single instruction stream, single data stream, would be able to perform, execute single set of instruction and on a single set of data at a time. Okay, what does that mean? There is one processor unit, all the functional units are, it is a single sequential system. Okay, it is a system that executes the instruction sequentially. So at a time, single instruction, and it works on single data. The instruction cannot work on multiple data. Single instruction, single data stream. Okay, so this type of system. So how parallel processing can be achieved in the system? By having more number of processing units, okay, more number of other functional units. And the second type of computer is SIMD, that is single instruction stream. S means single and M here means multiple. Okay, so single instruction stream, multiple data stream. This means the computer, it executes single instruction at a time, but it works on multiple data stream. Example, if there are operations like addition, subtraction, multiplication, and division. Okay, let's take this example. So this computer, okay, these type of SIMD computers can perform only addition, okay, at a time. Only addition or only subtraction or only multiplication or division. But this particular operation can be performed on different set of data. Okay, like adding A and B. And parallelly, the computer can execute perform the addition of C and D. Okay, and same time, parallelly, it can also perform the addition of some other data X and Y. Okay, so this way, single operation, single instruction stream, but multiple data stream. Okay, single instruction set can work on multiple data. Okay, so this type of computers uses many processing units, correct? Okay, how this instructions can work on multiple data at the same time. Okay, parallelly these operations can be done. So it needs many processing elements, but as all the processing elements receive single instruction set, the controlling can be easy. Okay, it uses a single control unit. These type of systems use a single control unit because different processing elements that process the same operation on a different set of data uses same instruction. A single control unit can manage this. And the third type of computer is multiple instruction stream, single data stream, MISD. Okay, this is multiple set of instructions working on single data, like addition. Okay, performing addition on A and B, and performing subtraction on the same data, and performing multiplication on the same data. So when the computer is capable of working on executing multiple instructions at the same time, okay, we prefer the computer to do the parallel processing on different type of data, right? Performing different operations on a single type of data, that is not preferred. Generally, we don't we don't design computer for such. So this type of computers having multiple instruction stream and single data stream, it is not feasible practically. Okay, so such systems have not been constructed. Okay, so not in practical use. And the fourth type of computer is multiple instruction stream, multiple data stream, MIMD. This uses multiple instruction stream, multiple instructions, and those multiple instructions work on multiple data. Okay, at the same time, multiple operations can be done. Like addition can be done on a particular data, and subtraction can be done on a different set of data. Okay, or addition, again the same operation, identical operation can be performed on different set of data. Okay, everything is possible in this multiple instruction stream, multiple data stream. Okay, so today's most multi-processors and multi-computer systems come under this category. Multiple instruction stream, multiple data stream, MIMD. So according to Flynn, the classification of computer based on the number of instructions and the number of data items that are manipulated simultaneously. The classifications are SISD, single instruction, single data stream, and single instruction, multiple data stream, multiple instruction, single data stream, and multiple instruction, multiple data stream. Three approaches are generally used for parallel processing. Okay, first one is pipelining, and then array processing, vector processing. So in this chapter, we are going to learn about these approaches in detail. Okay, the first one is pipelining. Pipelining, okay, it is a technique where arithmetic suboperations or the phases of instruction cycle overlap in execution. When we talk about pipelining, okay, this technique can be applied on arithmetic sub operations. If some arithmetic operations need to be performed, as we discussed, if it is add operation, okay, if adding on, it may be performing identical operations, okay, different units performing same operation on different data, or it may be different units performing different operations on different data. Okay, one of these categories, what we discussed. Okay, or different units performing same operations on the same data or different data. Okay, all this. So here arithmetic operations are subdivided. Okay, and the operations overlap when we consider arithmetic operations. Okay, overlapping is executed at the same time. One is started, and then before that finishes, the next operation starts. The processor starts the next operation. Okay, that is overlapping of operations. And in case of instruction, if it is instruction execution, we know the instruction execution is done in different phases. So the phases overlap. This technique is applied in arithmetic operations and instruction execution, okay, by overlapping them. This pipelining is a technique of decomposing a sequential process into sub-operations. And each sub-process is executed in a special dedicated segment that operates concurrently with all other segments. The operations are divided into sub-operations here. The sub-operations are executed in different segments. Okay, let's say we have a task, okay, to complete. There is a task or a process that need to be completed. It is divided into different small operations. Okay, so that parallel processing can be achieved and this task can be completed faster. Okay, otherwise, if it has to be executed in in the sequential steps, it takes a lot of time. Okay, so to reduce the time, okay, to speed up the process, it is divided into sub operations, let's say, and these sub operations are executed in different segments. Okay, special dedicated segment, each operation is performed, okay, executed in different segments. So S1 is the first segment. This executes the first sub operation, and the second operation, sub operation, is executed in segment 2, and segment 3 execute the third segment. Let's say it is divided into 3 segments here. Okay, so here pipeline, what is pipeline? It is a collection of all these processing elements. Okay, the processing elements here are segment S1, S2, and S3. These 3 processing elements that performs, operates parallelly, okay, with all the other segments. And pipeline is a collection of these processing elements through which binary information flows. So process 1 is completed by S1 and the information is given to S2. Okay, so information flows from S1 to S2 and S2 to S3. Finally, when S3, this operation is completed, we get the final result here. Okay, so after S3 is done, the final result. But the difference here is it allows the parallel processing of these operations. Okay, parallelly these segments operate S1, S2, and S3. So the pipeline can be visualized as a collection of processing elements through which binary information flows. The result obtained from the computation in each segment is transferred to the next segment in the pipeline. Okay, this is a pipeline through which the information flows between the segments. Okay, that performs the sub operations parallelly. Okay, so that is why it is called pipelining. Final result is obtained after the data have passed through all the segments. This way, pipelining supports parallel processing. And here is an example of this arithmetic operation, AI star BI plus C. Okay, the operation here is multiplying AI and BI and adding this result to C for I equal to 1 to 7. Okay, so here we have these operations, okay, to be repeated. correct, for every I equal to 1 to 7. First I is 1, so A1 into B1 plus C1, okay, it is Ci plus C1. And second time when I is 2, okay, I becomes 2 and A1 in A2 into B2 plus C2. Okay, so this way to perform this, if we perform this sequentially, first with I equal to 1, once this operation is over, second operation of A2 into B2 plus C2 starts. Okay, so to do this parallelly, it is divided into sub operations. So the sub operations here, what are the sub operations to perform this? This computation? AI need to be loaded into the memory operand, right? AI need to be loaded into one register. So here it is transferred to R1 and BI is transferred to R2. Okay, this is the sub operation 1. And the second sub operation is, now we have AIN, BIN, R1 and R2. So these need to be multiplied, multiplying R1 and R2 and storing it in R3. At the same time, CI is transferred to R4 for addition. Okay, so this is the second sub operation. And the third sub operation is, we have the result of R1 into R3 in, R1 into R2 in R3 and Ci in R4. So now adding R3 plus R4 and storing it in R5. Okay, so this is the third sub operation. It is divided into 3 sub operations here. So this figure shows this process, storing of AI in register R1 initially and storing of BI, memory operand BI into register R2. Okay, and the operation, this is done in first clock cycle, right? The first sub operation is moving AI to R1 and BI to R2. So this is the first sub operation in first 1 clock cycle. And the second operation is the multiplier circuit. We have the multiplier circuit that multiplies R1 and R2 and transfer it to R3. So getting the result of multiplication, multiplying R1 into R2 and storing it in R3 is the second sub operation. At the same time, CI is loaded into R4. Okay. And now the adder circuit adds R3 and R4 and stores the result in R5. So this is the third sub operation. And how this can be done parallelly when for every I is equal to 1 to 7. So to understand that, here we have this table. First, during the first clock cycle, 1, here we have segments. We have seen that this operation is divided into 3 sub operations. Okay, so this is stored in segment 1 and this is segment 2 and this is segment 3. So segment 1 has registers, okay, R1 and R2. You can consider it as processing elements, okay, segment 1, segment 2 and segment 3. So segment 1, the registers are R1 and R2. So A1 and B1. During the first clock cycle, A1 and B1 are transferred to R1 and R2. Okay. And what is the next operation? Multiplying these two, correct? So in the second clock cycle, the first operation is done. Second operation is multiplying this A1 into B1 and also transferring C1 to R4. Okay, but here when parallel processing is implemented at the same time during the second clock cycle, A2 and B2 are transferred because A1 and B1 that are already in R1 and R2 are multiplied and transferred to other register. So at the same time, A2 and B2 are transferred to R1 and R2. Okay, and the third clock cycle, okay, during the third clock cycle, what we have in R3, A1 and B1, A1 into B1, and what we have in C4 is R1, that is added. Okay, so this operation is done. A1 star B1 plus C1. So now as these are moved to register R5, the result is moved to R5, R2, R3 can be loaded with the multiplication of this. Okay, A2, B2, A2 into B2. Same time, C2 is loaded into R4. Okay, now as A2 and B2 are moved to A2 into B2, A2 and B2 are multiplied and moved to R3, A3 and B3 are loaded into R1 and R2. Okay, and the next clock cycle, during clock cycle 4, the same thing repeats. Okay, A2 into B2 plus C2, that is moved to R5. So now this A3 and B3 can be multiplied and moved to R3, and C3 can be loaded into R4. And as these are moved now, the same time A4 and B4 are loaded into R1 and R2. Okay, how we can do this parallelly, because these segments operate parallelly. Okay, these are all independent segments that operate parallelly. Only the information flows through the pipe. Okay, so the information that is in segment 1 is given to as an input to segment 2. So using that, it operates at the same time as these segments are independently operating. At the same time, segment 1, as it is free, the registers are free, it can load the next data input, okay, into the registers. Same way, segment 2, the finish its process and transfer the process to segment 3. So its registers are free. At the same time, during the same clock cycle, it can load the next input into these registers and perform the operation. So this way, as we have divided these operations into segments, it is possible to accomplish parallel processing here. Okay, so okay, in pipelining, these segments are connected, okay, by lines through which the information flows. So here, if you observe the first process, when I is equal to 1, A1 and B1 and C1 are used to perform this one, right? Complete this computation is A1 star B1 plus C1. It is completed after 3 clock cycles. 3 clock cycles are required for this. And after that, all the subsequent operations, okay, performing this computation on when I equal to 2, A2 into B2 plus C2 requires 1 clock cycle, and every next clock cycle completes 1 operation. Okay, so the time utilized for performing this complete operation is reduced. So you will understand it clearly here. Okay, these are the segments. Okay, here this is a 4-segment pipeline. We have 4 segments, S1, S2, S3 and S4. In between these segments, we have registers for storing the data temporarily and sending it to the other segment. Okay, and these registers are common clock pulse. A common clock pulse is applied to these registers. And S1, S2, S3 and S4 performs the operations parallelly, and data is transferred in between. So using these data, all the operations are performed parallelly here. And finally, this register R4 will have the final result. The behavior of a pipeline, okay, can be illustrated with a space-time diagram. We have seen the 4-segment pipeline here, okay, and this is the space-time diagram for 4-segment pipeline to understand the behavior of this pipeline. Okay, here the horizontal axis displays the time in clock cycles. Okay, so this is first clock cycle 1, 2, 3, 4. This way, horizontal axis displays the clock cycles. Okay, time in the clock cycles, and the vertical axis gives the segment number. And we have 6 tasks. Okay, T1, task T1, task T2, T3, T4, T5, and T6. And each task is divided into 4 sub-operations. Okay, 4 subtasks. So you see here T1 and the second sub-operation T1 and T1, 4 T1s. Okay, so that is that all these sub-operations run in different segments. Segment 1, the T1 operation that run in segment 1. Here this is a T1 operations run in segment 2. The sub-operation of T1 that run in segment 3 and the sub-operation of T1 run in segment 4. This way, All these 6 tasks are divided into 4 segments, that 4 sub operations that run in different segments, 4 segments. Clear? Okay, we have this horizontal axis shows the clock cycles. Here this shows the segments. We have 6 tasks here, okay, T1 to T6. Each task is divided into 4 sub operations. Okay, so 4 segments are used to complete this sub operations. If you observe this, task T1, okay, segment 1 executes task T1, okay, means the first sub operation of task T1, okay, during the first clock cycle. And during the second clock cycle, when this T1 is done, the segment 1 start executing the first sub operation of T2. At the same time, segment 2, because these segments operates parallelly, okay, and these are all independent. Okay, so this at the same time, okay, during second clock cycle, the second sub operation of task T1 is executed in segment 2. Okay, and during clock cycle 3, segment 1 move to task T3, the first sub operation of task T3, and segment 2 moves from T1 to T2. Okay, it takes task T2, and segment 3 starts the third operation of task T1, okay, the sub operation of task T1. And during clock 4, okay, clock cycle, fourth cycle, T4 is started in segment 1, and T3, the second sub operation of T3 is started in segment 2, and this segment 3 executes the third sub operation of T2, and fourth segment, okay, executes the task T1. Okay, and information flows between these segments, okay, through the pipe. So here, after the four clock cycles, the first task is completed. Okay, we have six tasks, and the first task is completed after 4 cycles. Okay, 4 clock cycles are required to complete the first operation. So that depends on the number of segments. As we have 4 segments, the first task is completed after 4 clock cycles. And how many clock cycles are needed to complete all the 6 operations now? Okay, as we have 6 operations, it is 4 for the first operation, and subsequent clock cycles complete the other operations. Okay, T2 is completed in clock cycle 5. T3 is completed here, okay, during the 6th clock cycle. And that way, during 9th clock cycle, T6 is done. So for completing the first operation, 4 clock cycles, and 4 plus this number of tasks minus 1 time, correct? Okay, so here the total time required to complete when there are k segments, okay, when the number of segments are k, and the number of tasks, okay, the number of tasks we have is n. Okay, we have n tasks, and the clock cycle time is TP. Okay, this TP we use for pipeline processing computers. In pipeline computers, the clock cycle time is referred to as TP. The number of segments is K, and the tasks are N. Okay, so we compute the total time taken here to complete this process is first process. To complete the first task, it is K time, right? That depends on the number of, if there are 4 segments, 4 clock cycles are needed. Okay, so the time taken is K, and the remaining tasks are completed in n minus 1 time. Okay, when there are n tasks, it is completed in n minus 1 time. So in our case, the number of segments are 4, and the number of tasks are 6. Okay, and the time is referred to as TP. Okay, the total clock cycle time is TP. So it is calculated as K plus n minus 1 time. Okay, K is the number of segments. So K is the time to complete the first task, and n minus 1 time is needed to complete the remaining task, n minus 1 task. Okay, so k plus n minus 1 TP is the time taken to complete n task in pipeline systems. And if we take a non-pipeline system, okay, let's say this system does not support parallel processing. Okay, so if 4 clock cycles are needed to compute one task, and then how many, what is the time needed to complete the n operations? So in non-pipeline system, let n is the number of tasks and Tn, okay, we say Tn is the number of the clock cycle time is referred to as Tn in non-pipeline system. Okay. Yeah, if we assume that, okay, here to complete the first task, it took 4 clock cycles. Okay, same way, every task take 4 cycles. Okay, so the time taken for every task is 4 of this time taken by this pipeline system. Okay, so it is 4 TP. Okay, so how it is done? N task, and each task, the time taken is K TP. Okay, so n into KTP. Okay, this is the time taken for completing the task in non-pipeline system. So here the speed up of a pipeline processing over an equivalent non-pipeline processing. Speed up ratio of a pipeline processing system over a non-pipeline processing system is S equal to N Tn by K plus N minus 1 Tp. Okay, K is the number of segments, N is the number of tasks, and Tp is the clock cycle time in pipeline process. And here in a non-pipeline system, N is the number of tasks and Tn is the time taken to complete the task. Okay, means the clock cycle time for every task, okay, is Tn in a non-pipeline system. So the ratio, speed up ratio of a pipeline processing system over non-pipeline processing is calculated as S equal to NTN by 4K plus N minus 1 TP. Okay, so here N is 6, number of tasks are 6, and Tn is equal to 4 TP here, right? Okay, so it is 6 into 4 TP by 4 plus 6 minus 1 into TP. It is, the ratio is 2.6. When the number of tasks need to be executed increases, the speed up ratio also increase. Okay, so this way using pipeline systems that divide the operations into different sub-operations. Those are executed in different dedicated segments that operate independently and parallel. This parallel processing can be achieved. The speed of the process can be improved. So here is a comparison between non-pipeline system and a pipeline system. So here we have calculated the speed up ratio. That's about pipeline systems. And here in the next class, we will be learning about arithmetic pipeline. Okay, when arithmetic operations are performed, how it is done here, okay, using pipeline. And when instructions are executed, okay, instruction pipeline. That helps the instruction when it goes through different phases, how it can be done parallelly using pipeline. Okay, so arithmetic pipeline, we have 2 subtopics here, arithmetic pipeline and instruction pipeline, that we will discuss in the next class. Any doubts here? Parallel processing is simultaneous data processing task. Okay, simultaneously performing the operations for the purpose of increasing the computational speed of a computer system. It increases the speed of a computer, okay, speed up the computer processing capability, and it increases the throughput, the amount of processing that can be accomplished during a given interval of time. So it can be achieved by having multiple functional units and distributing data among these multiple functional units. Okay, so this improves the parallel processing, improves the resource utilization. When we implement parallel processing, the resource utilization of a system can be improved. At the same time, all the resources, utilizing all the resources available, the task can be completed faster. So this speed up the process. Okay, but we require increased amount of hardware. Hardware need to be increased, so the complexity of the system increases. We need to have a complex control unit to control all these operations running parallelly in different units. Okay, this increases the cost of the system. So parallel processing is implemented in system where the execution time, okay, where the speed of the process is critical. Here we have seen the example how ALU is divided into different units, 8 units to perform these operations, okay, sub-operations parallelly to finish the task faster. And according to Flint's classification, we have discussed the types of computers that support parallel processing: single instruction stream, single data stream. Okay, in the computer with this organization can execute single instruction at a time with single data stream. So parallel processing can be achieved by adding more units, adding more processing elements and other control units. And the second type of computers is single instruction, multiple data. Okay, single instruction set can work on multiple data. So we have many processing elements to work on, parallelly perform all the processing. All these identical processing. Okay, single instruction stream that can work on multiple data stream. Like example, as I said, performing addition on different data. In parallelly, all the processes, okay, work on the same instruction. Instruction set is to add two numbers. Here data is different. Okay, but the third one is multiple instruction, single data. Okay, different processes run on perform different operations, but the data is, different data cannot be provided there. So such system is not feasible practically. Fourth one is multiple instruction, multiple data stream. Okay, here multiple instruction, multiple operations can be performed on multiple data parallelly. Okay, so many microprocessors and microcomputers come under this category. Different approaches for implementing this parallel processing are pipelining, array processing, and vector processing. Pipelining is a technique of decomposing sequential process into sub-operations, and these operations are executed in different segments, okay, that operate independently and parallelly, and information flows through. Okay, this collection of these segments form a pipeline, and information flow through this line from one segment to another segment. So when all these segments complete the operation, the final result is obtained. Here we have seen this example, okay, how parallelly all these operations can be done. Okay, here it's a repeated operation, just performing A star B plus C on different data. Okay, so what type of configuration this is? Can anybody tell me among SISD, SIMD, what type of configuration is performing A star B plus C on different data? It is same instruction on different data, right? Single instruction, multiple data, SIMD configuration. Okay, the computer that performs this operation parallelly come under SIMD, single instruction, SIMD, single instruction, multiple data. Okay, the instruction is same to perform this. This is done on different data for I equal to 1, I to 7. And this is a 4-segment pipeline, how it is connected, and through this pipeline, information flows between the segments. To understand the behavior of the pipeline, we have seen the space-time diagram and how these tasks are divided into sub-tasks, okay, and executed in different segments. When we compare it with non-pipeline system, okay, what is the speed up of a pipeline processing system over a non-pipeline processing system? Okay, that we have seen here. If you have any doubts, you can ask me. Meanwhile, let me check the attendance. Yes, I have checked the attendance. Any doubts? Otherwise, we will leave. No doubts? Okay. Thank you. You can leave.